Okay, now, this exact solutions for Navier-Stokes equation. See, the case for which exact solutions are available, the most simple of them is for unidirectional flows. For unidirectional flows, there are many flow problems where the flow is in only one direction, and let us call it that is the x direction. It need not be a straight line, the direction need not be a straight line, it can be curved also. That means, we can have a x which is curved. And further, in many situations these unidirectional flows are found to be independent of that particular direction. That is, if the flow is in x direction, then it is found that this flow is independent of x. The flow is in the x direction, but it is independent of x. Whatever change is taking place only in a particular cross section in y and z, and approximately this type of flow you always find, say, in a pipe. If you exclude the end part of the pipe, that is where the flow is entering the pipe and where the flow is going out of the pipe, if you exclude those regions, some part just immediately after the entrance and some part just before the exit, then in the major part of the pipe the flow is almost like this. That flow is only in one direction, and in particularly it is independent of that direction. So, we assume for flow which are unidirectional flows So, unidirectional flow, that means of course, and that is the direction we are taking as x. The direction of flow itself we are calling x. Let us call that x. That means, we have only x component of velocity, the y and z component of velocity are 0 for these problems, and the y and z component of velocity is 0 and the x component of velocity is independent of x, meaning we have the x component, that is u is function of y and z only, and v equal to 0, w equal to 0. The three component of the vector velocity u are like this. Now, let us see what happens to the equations then. What happens to equation then? The continuity equation is now very simple, du dx equal to 0. There is no v, no w. So, the continuity equation, the divergence of u is simply du dx equal to 0, which is already we have considered. So, the continuity equation is basically automatically satisfied by this. Anyway, still write continuity equation. And this is satisfied by default. So, we really do not need this equation, this is already been satisfied. The momentum equation, let us write in component form. Now, the first x component of momentum equation, x component of momentum equation, we will call it x momentum equation. The x component of equation, if you look to this equation, the x component of momentum equation will be you will the rho will take it to the right hand side, du dt plus u du dx plus v du dy plus w du dz equal to that modified pressure, in terms of that modified pressure, plus nu Laplacian of u. Now, look here, in this term and these terms are 0, this term is 0, this term is 0, v and w are 0. So, only this remains, and in the Laplacian also only one term will remain. So, this will one term, not two terms will remain. Laplacian of u is d2 u dx2, since du dx is 0, d2 u dx2 is 0. So, this is we have d2 u so this is the equation that we have now. Similarly, if you write the y and z component of momentum equation, what is it? Let us write once all the left hand side is and all these equations they contain v. So, all of them are 0, all the terms are 0, this is 0, this is 0, this is 0, this is 0 and this all 0. So, it gives only and similarly the z momentum will also come as z momentum will give that is that modified pressure is not changing in the y and z direction. So, the practically the equation that we now have is this, the equation that we need to solve that x momentum equation du dt plus u By the way, this term is also 0. So, sorry, this I have not written 0, du dx is 0. So, this is also 0. This you, so this term is not there. Since pressure is now a function of x and t only, pressure is not function of y and z, we will write it also if the flow is steady, then the left hand side is 0. If the flow is steady, then this left hand side is also 0, and then the pressure becomes only a function of x, and this can be written as ordinary derivative. Oh, plus. This will make a small modification. See this when you defined that modified pressure, actually we made a something this P by rho plus psi. Instead of that we wrote only P, this we will write as P by rho only. So, that otherwise the definition of pressure will change. So, this will write as rho, please, because the original pressure term contained P by rho, we would like to retain the same form. So, that modified pressure will also retain P by rho. Okay. So, as a result, what will happen in this equation, there will be 1 by rho. All these equations there will be 1 by rho as we had original equation. These also you can have 1 by rho and 1 by rho. It really does not matter, as far as your mathematics and all is concerned, this rho is a constant, so it hardly matters, but we want to retain the same form, that is what we are writing that rho. And of course, this rho we can take it to this side and we can write it as mu. Okay. See, since the flow velocity u is independent of x, that implies that this pressure gradient dp dx will also be independent of x. P itself is not independent of x, but dp dx will be independent of x, because if dp dx is not independent of x, then u cannot remain independent of x. So, this dp dx is independent of x, and in general we can write dp dx. If we look to this equation, this dp dx can be written as a function of temperature time alone, and here it is just a constant. So, we will write that constant as or no, let us that make it minus. Where g is dp dx. Okay. G is minus dp dx, which will be a function of time for an unsteady flow, but for a steady flow it is a constant. So, finally, this is the equation that we need to solve for this problem. Okay. Now, you see this equation is linear, that is the basic idea. We have made the equations linear, which are originally non-linear because of that convex acceleration. We have assumed a case, or we have approximated some flow problems, so that the convective term is basically vanished and the flow has become linear. I think this equation you have solved earlier. I do not know whether you have written the equation in this form or not, but of course, you derived the equation from by considering free body diagram for that particular problem, and then obtained this equation, and I think you solved pipe flow in your school physics. No, okay, might be. I thought that you did something like that. Anyway, it may not be. Now, we will apply this first of all for a common problem which is classically known as Hazen-Poiseuille problem, Hazen-Poiseuille flow, which is equivalent to, or which is similar to flow in a very long pipe or long duct, but in which the end effects are not considered. That means, this solution will not be valid for near the entry or near the exit. Okay. So, flow through a long duct or pipe. Of radius say a. So, this is an unidirectional flow, this is an unidirectional flow, and flow velocity independent of the distance along flow direction. Excluding end effects, flow is steady. Near the entrance and near the exit, flow never reaches a steady condition, but after certain distance from where the flow started, after certain distance the flow reaches a developed state and is practically time independent. So, remember that the solution that we will be getting is not valid near the entry and near the exit. Okay. So, if you have say very long duct, so this is entry. So, some portion near the entry and some portion near the exit is not valid in this entry and this exit part. This equation does not hold. Okay, the equation of motion for this is the Laplacian operator in the cross sectional plane. The Laplacian operator, this left hand side is the Laplacian in the cross sectional plane. Now, you see this y and z or x y z is not a very good or appropriate coordinate system for this. For this type of problem, the appropriate coordinate system is x r theta. X is of course again the x direction. So, the cross section is represented by r theta. Now, from our physical observation or from general sense, we can say that this flow when is developed is basically axisymmetric, that whatever the theta is in any particular theta direction, the flow will be same in all theta direction. There cannot be any theta dependence. So, what is the Laplacian operator now? The Laplacian operator will be in terms of r and theta, and since theta is independent, so the Laplacian operator will contain only r derivative. And in x r theta system, this equation becomes 1 by r d d r. See, we need not even write partial derivative, because there is no variation in x, that is already the case. The flow is independent of flow direction and there is no change in theta direction also. So, only change in r direction. So, it is the ordinary derivative. The Laplacian operator in r and theta would have contained another term for theta derivative, but that is 0. Now, can you solve this equation? This is an ordinary differential equation with the right hand side is a constant. So, it is very easy to solve or very easy to integrate. The integrated result is, that is, if you integrate that equation twice, we will get as u equal to g by 4 mu minus r square plus a log r those a and b are two constant of integration. Those you have to now find using the boundary condition. Now, what boundary condition we can apply here? If we consider this duct of radius A, then where the flow is in contact with the duct, that is the wall, and at that there will be no slip. So, you can say u equal to 0 when r equal to A. Any other boundary condition we can say here? Really no, that is the only one boundary we have. Then two unknown constant, how do we get two value? For the second one, look that this term, the second term a log r becomes singular at r equal to 0. Log 0 is not defined. So, the second term becomes singular at r equal to 0. The velocity is there undefined, but in a real practical problem, how we are getting this flow? We are applying certain amount of pressure difference between 2 points in the flow. Okay. So, obviously, you are applying a certain finite amount of force. If you look in terms of a dynamic problem, you are applying a finite amount of force in this flow. Applying a finite amount of force, there is no physical reason that why should there be a singularity somewhere. So, the singularity cannot exist. This solution gives a singularity at r equal to 0, but our physical reasoning says that there cannot be any singularity in this flow. How is it that possible? That is possible if this term does not exist, if this term is not there, that means A is 0. If this term is not there, then this singularity does not arise. So, this A is 0. If you want, to can write that and then we have no slip boundary condition u equal to 0 at r equal to A. And then what do we get? We get B equal to G by 4 mu A square. Okay. This gives B equal to G by 4 mu and hence the finally we can write that solution to be u equal to G by 4 mu you can see that is a parabolic distribution or a paraboloid, if we consider the entire pipe with why
instead of a square, that is g by 4 mu a square.
sorry
So in the initial solution, b is inside bracket and b is again g by 4 mu a square. So inside the bracket there will be one small g.
but you, oh no, b for b we have already taken out g by 4 mu. So, this b will not have this. I just put that value of r equal to 0 and wrote this, but this g by 4 mu is already taken out. So, it is not. Okay, this is a, so the flow velocity within the at a cross section is distributed as a paraboloid of revolution, or if you just consider one particular value of theta as a parabola. And it has a maximum at the axis r equal to 0 and it becomes 0 at the wall. Okay. Now, it is quite often the average flow velocity is an important quantity. We would like to show that if there are no variation across the pipe, because most often we consider that okay, the flow velocity in a pipe we call only one velocity. Okay. In that case, it should be the average flow velocity. Now, what will be the average flow velocity? Okay, you can find an average distribution, but we will find the average in a much simpler way, or we will look to this. How much is the volume flow through this pipe? What is the volume flow rate or volume flux? That is the total volume passing a particular cross section. See, if you are analyzing a pipe or designing a pipe, you should know that how much volume this pipe will allow. So, the volume flow rate, how do you get the volume flow rate? Okay. Tell me how much is that? Volume flow rate or volume flux? Most often it is written as Q, discharge, capital Q, sorry, this is capital Q. How much is it? U, area is 2 pi r dr, integration from 0 to a. This will come as pi g a to the power 4 by 8 mu. So, we can, instead of writing this g, we now can write it in terms of some pressure or the modified pressure, to be precise. And that g can be written as, see, if we consider that at 2 point at 2 station 1 and 2, the distance between that is length L, then the pressure gradient is P 1 minus P 2 by L. So, this can be written as if we consider a length of L of the tube and the pressure at that 2 point is P 1 and P 2.
So, g is the derivative of
modified, obviously modified pressure. So, as an example, see, if you are considering a pipe which is inclined and then length, you should take the effect of gravitational force also within that modified pressure. Do not forget that this pressure itself contains that gravitational effect or the body force effect. You are not writing them separately, but that body force is present within this pressure itself. So, this is just not simply the fluid static pressure plus the effect of body force, that is also within pressure. So, there might be something where there is, just think about a situation like you might have seen that from some dam or something the water is coming out and you are not applying any pressure difference, it is open to atmosphere. On an inclined surface the water is coming out, both is exposed to atmosphere. So, it is the pressure is basically atmosphere at all the points. So, there is practically no pressure difference, but there is a difference in modified pressure, because there is a difference in the gravitational effect, gravitational force. And then this average flow velocity can be defined as we will call it simply u bar is q by a. So, what is that, what that becomes? Or in terms of g, at least we will write g because that is shorter to write. Okay. In terms of g, it is g square by 2. G square by 8 mu, g square by 8 mu. Can you write that as u maximum by 2? You can see from that solution u equal to g by 4 mu a square minus r square. When r is 0, you get u max, maximum u velocity, which is g by 4 mu a square. So, it is that half of that, the average velocity half of the maximum velocity. What is the shear stress acting on the wall? Shear stress on the wall. How much it will be? In this case, the expression will be mu into or minus mu into du dr. In general, the shear stress is tau r theta, wall shear stress is tau r theta. So, it will contains a theta derivative also if you write the strain rate for r theta, but since theta derivatives are 0, it is coming as du dr only. Stress on the fluid is mu du dr, stress on the wall is minus mu du dr, and how much is this? This comes as this du dr of course is at r equal to a. The du dr is to be evaluated at r equal to a, because you are finding stress on the wall, and this comes as half of G A. Often expressed in terms of average velocity for mu u bar by a. So, total frictional force on that section of the pipe, how much will be total sectional frictional force on the section of pipe? Okay, this shear stress is to be multiplied by the area on which it is acting, and area of that on which area it is acting. The curved area, and that area will be how much? 2 pi a into L. So, this is that how much is that? You can substitute and you can see this will be something pi the rate of energy dissipation is another important parameter, and it is also required if you want to solve a temperature field. Once the velocity is known, you can solve for the temperature, and then of course, this term will be required, rate of energy dissipation, say per unit mass or per unit volume, let us say per unit mass. This is the term phi is this becomes So, total energy dissipated over this section of length L this has to be integrated over the length sorry, this is nothing, actually by mistake I wrote the r twice, 2 pi r L dr. Okay, dissipation over the length. So, it becomes volume. So, we have to multiply the one more row. The first term we wrote here for unit mass. So, another row is for that to make it unit volume and of course, integrate from E. And this will come as pi L E4 8 in terms of the other parameters L Q G. So, this much of energy is lost over the length of L, and to maintain the flow of course, you have to supplement it. Okay, that is being supplemented by maintaining that pressure difference. Some non-dimensional parameter are used to express this frictional effect in this flow, and they are defined in this way. One is Darcy friction factor, which is okay, we will denote by lambda and is defined by this. This is a popular parameter in hydraulics and other fluid machineries, aerodynamics, but not used in aerodynamics. But anyway, this is practically a hydraulic problem, not an aerodynamical problem. So, we will be using this Darcy friction factor. This is the definition, and how much it will come? Just substitute those values and see. It will come to be this 64 y RED, where this RED is a Reynolds number based on diameter, the Reynolds number based on diameter. In case the pipe is not circular, then this diameter is to be treated as hydraulic diameter. Another friction factor is defined, which is again in hydraulic they call it fanning friction factor, or we will call it skin friction coefficient. The skin friction coefficient is of course a very popular parameter or in aerodynamics. This definition is, say, or most often we will call it tau w by half rho u square. Tau w, that is wall shear stress, by half rho u square. And obviously, from here it will be 1/4 of this lambda. This is by definition, this we will write as C f equal to lambda by 4 in this case. And often this product of the skin friction coefficient and this Reynolds number based on diameter, this RED, the product of these two is called Poiseuille number. Poiseuille number PO is this CF into RED, and this of course in this case is becoming 16. As you can see, this skin friction or this skin friction coefficient or the wall shear stress is an extremely important parameter in aerodynamics. If you look back to our original discussion in the first and second lectures, we said that our main aim is to find the force that is acting on the body as the body moves through a fluid, or alternatively if fluid moves over the body. Obviously, that the force may come from different sources, that we also talked at that time. One of the source of this force is definitely this frictional force or the viscous effect, which is the wall shear stress. Of course, that is not the only force, there will be other contribution from the other type of pressure distribution and all, but this is also one of the major component or important component. And in particularly for say commercial vehicles or transport vehicles, the drag force is predominantly comes from this wall shear stress. So, if you think about a transport aircraft, then the drag force that is acting on that transport aircraft is mostly from this wall shear stress or friction, viscous effect. And obviously, see that determines how much engine power you should have, so that you can take your aircraft, and hence how much fuel you need to consume, what type of engine you are going to have, how much fuel you would have to consume. So, finding that wall shear stress on the aircraft is of course a very important or fundamental task of aerodynamics. Okay, before we switch to some other topics, we will solve a couple of more such problem where we can solve the Navier-Stokes equation mathematically. Then of course, since we are interested in certain type of problems where Navier-Stokes equation cannot be solved mathematically or analytically, we will look for alternatives.